Hello everyone, and welcome to Robotics 2. Today I'm going to do a problem that I had in a homework recently for forward kinematics. Actually a couple of problems, they'll be in other videos. But just for forward kinematics, how can you lay out the forward kinematic chain for this arm basically by just looking at it? In previous videos for Robotics 1, I actually derived how to go from this point to this point to this point, and it was a very laborious process. But if you're just trying to lay out the forward kinematics for a robotic manipulator, it really doesn't have to be that complicated. So right here we have a two-link manipulator. We have the initial axis, we'll call the inertial axis, or U, of X, Y, and Z. And then we have the axis on the joint of this arm right here, which we'll call axis 1, Y1, X1. And then we have axis 2, which is on the joint or link of this arm right here. And they rotate theta 1 and theta 2. And they have lengths of D2, D1, so on and so forth. Right here, this label is UURH, is actually the label for this. You might not be able to see it, but there's a line drawn right across here. It's not a label for this line. This distance is D2. But this line, this very light vector from this point to this point, is the vector UURH. So the vector from measured in U from U to H. That's what that is. So this is measured in, and this is the start point and the end point. That's how this notation works. So, setting this up, looking at the first equation here. Actually, I'm going to do this a little bit differently. To set this up, you have to do just a basic vector addition. So we have a vector from this link to this link and a vector from this link to this link, which is 2, 2RA. So measured into from 2 to H, and then 1, 1, R2, which is measured into from 1 to 2, from axis 1 to 2. So the total vector from this point to this point is UUR1, this vector, plus U1, R2, which would be the vector from here to there, UUR1, which is this is the matrix from the axis U from U to 1, measured in axis U from U to 1. So basically, from this axis to this axis, and as you can see, that's just a rotation. And then in this one, it's from here to there, and then from this one, it's from here to there, which are all those vectors that I've shown. Now, if we break this up a little bit more, from UUR1, the rotational vector for this is nothing, because there's no translation anywhere along this from going from this axis U to the axis 1, because they have the identical origin. So UUR1 is 0, 0, 0, because there's no translation along the X, Y, or Z axis. But over here, we do have a transformation matrix, so a rotation, and then the translation 1, 1, R2 from this point to this point. And the same thing is true for over here. So we have a translation from 2 into U, or from U to 2, however you want to look at that. This is basically set up so that you can cancel the subscript and superscript, and you know that you'll end up with this equaling, this will essentially go to URH in frame 2, which is the vector right here, which we're looking for. Excuse me. So that's how this cancellation works, why we have these subscripts set up like this. You might like it 2 to U. It doesn't really matter if you like frame 2, axis 2 measured in frame U or something like that, or reverse. It's pretty much arbitrary. I just like this notation because you're able to cancel these superscripts if you're kind of lost about where the vectors are. Okay, so in actually doing this, so this is all 0, so we're just going to kill this. The transformation matrix from U to 1, from U to 1, well, you see that while they're on the same location and there's no translation from there to there, you do have a rotation from into 1, which is a rotation about Z, a positive rotation, because right-hand rule, about Z, of theta 1, which is the rotation right here, and then you have the translation from D1, or of D1, to get into this second link and get the vector of U1R2, basically right along here. So we just figured out how to measure the vector 1, 1, R2 with respect to u in this final axis. So you take y1, y1 in its normal configuration, but you have to rotate it and then translate it to get to this point right here. And that's how that works. Now, if you're up here at this point, or going from here to h, or yeah, from here to h, you have to do a rotation about z of theta 1, and then a translation, a rotation about z of theta 1, and then a rotation about z of theta 2, and then a rotation of d2. So you can see how the rotations propagate, because this rotation, when you're on this point, the displacement of this point out here will be a combination of this theta and this theta. That's why you include both these thetas. So this gets you to this second link, and then this gets you to this point right here. That's kind of vague. I wish I could draw this out a little bit more, but I don't really have time. So hopefully you can all kind of see that. We're basically doing a vector addition, and we're just defining each vector as we go along. So we have this vector and this vector. We add them together, and we get this point with respect to the inertial axis u. That's what's going on. So you first do the translations, basically, translational vector from the inertial axis into the whatever other axis you say. You could put y1 way out here and it wouldn't change anything. Per se, you'd have a translation of x and y somewhere in there. You then have a rotation to get it in form, and then a translation along some axis, right here. In this case, we translate along the x-axis of d1, and then you have a translation that is equal to both of the, or a rotation equal to these two rotations right here, and then a translation along some axis, x2, of d2, and you get that point. So it's just a continue looking at it and saying, oh, okay, here we go along. Now, that's actually kind of the harder way to do it. You can do this with homogeneous transformations, which is basically the vector of something, something, something all over ones, or 0, 1. So hopefully your professors introduce you to homogeneous transformations, and I've done that in one of these videos before. But what you can do there is say, okay, well, to get to UURH, you have a homogeneous transformation around z of theta, a homogeneous translation, a homogeneous rotation around theta, sorry, a homogeneous translation of d1, moving along d1, another rotation right here, and then the last vector distance. I mean, you could say h trans d2 over whatever it is, but then you would end up with basically a vector equal to a matrix. So you would have to add in another vector or another matrix at the end of this in order to have it all work out correctly. Because you would have a matrix equal to a vector, I'm sorry. So you would have to add on another vector of like 0, 0, 1 to make this work correctly. So it's best to just take the final translational vector, and if you were thinking of using an h-trans, just cross out the h-trans and use the vector. That's an easy way to think about it. There's a much more legitimate mathematical reason for that, but as far as doing this homework, it's easier to remember right as this. Okay, and this should technically have a 1 underneath here. This is kind of sloppy notation because it's so quick, but since these are homogeneous vectors, they need to have a 1 on the bottom, but it really doesn't matter at all. And then if you wanted to solve this out completely in MATLAB, hopefully you have the homogeneous rotational matrices and translational matrices stored up, and you can just plug them in and have it solve it out for you, because that's just kind of tedious. But that's the basic way to look at a forward kinematic manipulator and basically extract a vector addition method definition of the forward kinematics and a homogeneous transformation definition of the forward kinematics. So hopefully that wasn't too convoluted for you, but basically you look at it and say, okay, I'm right here, I gotta rotate a little bit, then I gotta translate a little bit, then I gotta rotate a little bit, then I gotta translate a little bit. That's pretty much what the homogeneous is. And then in the vector addition, you take each vector, you define it, and then you add them together. That is the very basic, most boiled way down way I could put this. Alrighty.